So today we're going to look at pretty much a full recap of the quadratics unit, or at very least chapter 4 of the quadratics unit. That's where we were, of course, using several different methods to solve for different x-intercepts. Let's get going. So today's plan is we're going to ensure that we have a complete understanding of all 4 of the methods that we've covered for solving for the roots of a quadratic function. So that includes graphing, in other words, using your graphing calculator, factoring, which had 3 different methods built in, vertex form / square root method. This one didn't really have a great name, but if it's in vertex form, you'll use it. We'll go over that one again. And then last but definitely not least, of course, the quadratic formula. We'll also look at a few more problem-solving questions. I might get you to try one or 2 of them. I think there's 2 or 3 of them in here on your own, but I definitely will go over one of them with you. We'll get to there when we get there, of course, and then you'll have lots of practice time today, and it includes our assignment for this chapter. Anyway, let's get going. So just a few hints for graphing. And by the way, this is in our printed note booklet. It's page 35, but just a few hints for graphing. Always, whenever you start graphing a quadratic, you should always start on a standard window. In case you're not aware on how to get to a standard window, on your TI-83 calculator, if you press the zoom button, which is the middle button up by the window, and then go down to where it says zoom standard, that resets your window back to a standard window. And by standard window, I just mean it goes from -10 to +10, both in the X direction and in the Y direction, right? It's just a very workable window. Like 90% of the problems will have solutions within that window. But every now and then we do have to change our window to something different. We'll get to that in just a second here. So remember, we're looking for the roots in chapter 4, of course, which is just a fancier way of saying the x-intercepts. Our y min and y max need to be negative and positive respectively, of course, to see them. What that basically means is like you have to have your lowest y value to be something below 0 and your highest y value to be something above 0. So that way, you can actually see where it's crossing your x-axis. In other words, you can find your x-intercepts. Kind of a silly thing to say, but it's just important to note. Now, this is a big one. If you can't see any x-intercepts, if you graph this under a standard window and you're not seeing anything, you might not even see anything on your function at all. There's a little bit of a trick you can do, and this is going to seem silly because you're trying to get away from doing work by using a graphing calculator to begin with. But you can start by finding the vertex algebraically. Just remember that's x equals -b/2a. And then you use that x as the midpoint for your x min and x max. So let's say you use this function here, and you found that your vertex is actually x equals, let's say, 25, right? If x is 25, if that's your vertex, it's no wonder why you can't see your x-intercepts in a standard window, because your x-intercepts aren't going to fall between -10 and +10, at least not necessarily. So what you can do from that is we can understand that your vertex, at least the x part of your vertex, will be the midpoint for your x min and x max. So maybe if I found that I had a vertex that was x equals 25, maybe I'd set my x min to be like 0, and then my x max I could set to be like 50, right? Still leave your y min and y max as a negative and positive number respectively, just so you can still see your roots. But just kind of play around with it that way. It's more of an art than a science to find these kind of things. You have to just kind of play around with them. But it is a useful tip if you do that. I know some people are probably even thinking right now, and I don't know where you would have learned this in previous math courses or what, but if you press the zoom button on your calculator and you scroll down to, I think it's 0, it'll say zoom fit. Apparently, this is designed to basically look at your function that you've graphed and try to fit it into the window. I'll be honest, this only works like half the time for me. I use this sometimes and it's like, oh, okay, that actually changed the window to something more reasonable. But usually like 9 times out of 10, you have to just, use this, to be honest, right? So you just find your vertex. It'd be a little bit easier. That way you're taking out the guesswork. But hey, I guess, if you want to try zoom fit, whatever, do whatever you need. That's what I'm trying to say here. Anyway, let's see a real example with this. So solve the following quadratic graphically to the nearest hundredth. So in other words, tell me what your x-intercepts are to the nearest hundredth. Pause the video here, give it a try, and I'll go over it in just a second. All right, so hopefully you gave that an honest try. If you throw this in your graphing calculator with a standard window, you're only going to see one of the x-intercepts. There's going to be another x-intercept that's going to happen just kind of outside the window. You don't have to use that vertex method thing here where you go like, oh, where's my vertex? And then set that as a midpoint, because it's going to be pretty clear more or less where it is. But I'll be honest, what I did was I changed my x min to be about -20. And then I changed my x max I just kept it as 10, I should say. I just left it at 10. Anyway, when I changed my window on that, I still left y min as being the standard -10 and y max as still being the standard +10. When I actually graphed this with this new window, what I found was I had two x-intercepts that were clearly visible within that window. The first one, the one on the left, I should say, is x equals to the nearest hundredth 10.72. And then the one on the right was x equals -0.28. So again, I just had to slightly change my window in order to see these. If you really, really wanted to, you could have found the vertex and then use that as a midway point, but you'd see that the vertex is just going to be x equals -b, which is going to be +22, divided by 2 times a, so divided by 2 times -2. If you do that, that's going to be 22 divided by -4, which I'm pretty sure is -5.5. So that could have been used as a pretty good midpoint. Obviously, I went way too low with this x min of being -20, but hey, at least I was able to see the other one. That's basically the idea. Anyway, moving on. Here we go. Factoring. This is like the biggest, and I would argue almost most important part of chapter 4 is understanding how to factor a quadratic, because factoring, it provides one of the best ways of actually finding your x-intercepts. It actually spells it out algebraically very, very well. Just remember, there are 3 types of functions that you'll be expected to factor. There's these ones right here, just a standard form quadratic with 1 as your a value. I call these just sum product rule questions. This is where you're looking for 2 numbers. I call them a p and a q. You're looking for 2 numbers, p and q, with a sum of b and a product of c. Once you find those 2 numbers, this factors just straight to x plus p times x plus q. We've done a bunch like this. These are nice because once you find your sum product and once you find what your p and your q are, you're done. You just put it like this and you got it. You got it factored. No big deal, right? The next kind is nobody's favorite. It's called, or at least what I call it, is the adapted sum product rule. It's very much like the first one, but it's got a million extra steps. Your b value is still your sum, but because we have an a value that is not equal to 1, your product is actually equal to a times c. So you're going to have to find, once again, a p and a q that has a sum of b, but a product of a times c. Once you find that p and q, you're not actually done. You can't just jump right to an answer like you could with this one. You have to split apart the middle term. So you have to go ax squared and then use your p and q to split apart the bx. So it'll be plus px and then plus qx and then plus c. So notice I just split apart the bx. You then put brackets around the first 2 terms, brackets around the second 2 terms, and then you do something called factoring by grouping, where you say, hey, what can I pull out of these? And then what can I pull out of these? And you should get things that match. Bingo, bango, bongo, you go from there, right? Anyway, we can go over a question like that. I think we do have at least one like that in here today, but we'll go over that when we get there. The last one, and everyone always forgets that this is even a thing, it's called difference of squares. Basically, if you have 2 numbers that are square rootable, in other words, you can take the square root of them, and you're just subtracting those 2 numbers together, you can actually jump straight to factored form. This is just going to be the square root of the first number. So if the first number is a squared, it would be the square root of that, which is just a, plus the square root of the second number, which is just b, multiplied by itself again, except instead of a plus b, it's a minus b. Don't forget that step, right? So to factor this, you just take the square root of each piece and multiply the added version times the minus version, basically, just to simplify that down, right? Now, when it's fully factored, just set each piece equal to 0. So like if we looked at this one, for instance, just say, oh, a plus b equals 0. Solve for your missing pieces. The solution to each piece will be a root, or in other words, an x-intercept. Whew, that was a long-winded explanation for this. We're going to do a few examples. I want you guys to give them a shot. So the very first one here, use factoring to find the roots of that quadratic right there. So we're looking for the roots, and I want you to use factoring. Pause the video here, give it a try. All right, I'm going to go over this one now. This is going to be an adapted sum product rule question because we have an a value that is not 1. Now, I'm going to be honest here. If you're really, really, really keen, you might see that we could factor out the 3 first, because all 3 of these numbers are divisible by 3. If you do that, you'll have 3 times x squared plus 5x plus 6. And then look at this. This is just a normal sum product rule question. You could basically just use the normal sum product rule on this and you'd be done. I'm going to pretend I didn't see that. If you did see that, great job. Honestly, that is very, very keen. I'm going to pretend, though, that this is just a normal adapted sum product rule question. So I'm going to look for 2 numbers with a sum of 15 and a product of 3 times 18. And 3 times 18, just by the way, is 54. There we go, 54. So I have to ask myself, what two numbers add together to give me 15, but multiply together to give me 54? Spare you the trouble, just if you think about it for a little while, the answer is going to be 9 and 6, because 9 plus 6 is 15. 9 times 6 is 54. So since it was 9 and 6, I'm going to use those two numbers to split apart the middle term. So this will become 3x squared plus 9x plus 6x plus 18. Once I split apart the middle term, I do something called factoring by grouping. Let me just change to a blue pen here. Here we go. I basically put brackets around the first two terms, and then I put brackets around the second two terms, not including the middle sign here. So I keep the plus just on its own. It's just hanging out right there. Then I factor out what I can from the first two. Ask yourself, what comes out of 3x squared and 9x? Well, the common factor between those would be 3x. So I'll pull a 3x out. If I divide each of these by 3x, this just leaves me with x plus 9x divided by 3x is just 3. So 3x times 9x plus 3. That's what I have for this piece. Then plus, ask myself, what can I factor out of these guys? Well, I could take a 6 out of both of those. Not a 6x, just 6. So if I take 6 out of there, this is going to leave me with x plus 18 divided by 6 is 3. Now, here's really good news. When you see that in the brackets, you have two things that match. That's the way of the question telling you that you've done this correctly, right? So since there's x plus 3 on both of these, I can just say now that I have x plus 3 times 3x plus 6. And that is now completely factored. So this expression right here, x plus 3 times 3x plus 6, that is now my factored form. However, we got one more step to do here. We wanted to find the roots. This is where you set this thing equal to 0. And you have to ask yourself, when is something times something equal to 0? Well, it's just when either this piece equals 0, so x plus 3 equals 0, or it's when this piece equals 0, 3x plus 6 equals 0. Solve each of those two expressions, and that'll tell you what your two x-intercepts are. For this first one, we just have to minus 3 on both sides, so that gives me x equals negative 3. Boom, right there. That's one of my x-intercepts. This next one's a little trickier, so if I minus 6 on both sides, this gives me 3x equals negative 6. Then divide by 3 on both sides, and you have x equals negative 6 divided by 3 is negative 2. So x is negative 3 and x is negative 2. Right there, those are our two x-intercepts. Now, if I go back to this, like remember at the beginning I said, oh, if you're really keen, you can see you just took a 3 out of there. I'll actually walk you through that one as well. So pretending we didn't do all this stuff on the left, I can show you how we'd finish that off. That's just a normal sum product rule at that point. So you'd just be looking for two numbers with a sum of 5 and a product of 6. Well, two numbers that add together to be 5 but multiply together to be 6 would be 3 and 2. So I could write this as 3 times x plus 3 times x plus 2, which, believe it or not, is the exact same thing that we got here, just slightly differently factored. They just pulled the 3 out of it and put it on the outside, and I'll prove it to you. If we say that that's equal to 0, we have to ask ourselves, when is each piece equal to 0? Well, 3 is our first piece here. 3 is never equal to 0. That doesn't make any sense. Like 3 would never be 0. It's 3. It's not 0. You know what I mean? Like it just doesn't make any sense. But this guy, x plus 3, that'll equal 0 when x is negative 3. This piece, x plus 2, that'll equal 0 when x is negative 2. And what do you know? We got the exact same answers as if we did it using the adapted sum product rule. Basically, what I'm trying to spit out here is it works both ways. You can do it one way or another. Next example. This one is super beefy. I want you to just pause the video here. You don't have to solve this one, but pause the video here and think, what kind of factoring method would we use? All right, so this is a really, really tough one. Some people would be tempted just to multiply the whole thing through. So they'd go oh, they'd say, all right, 16 times a plus 3 times a plus 3, that's a 3 there, minus 4 times a plus 1 times a plus 1, and then you got to double dip this through. It'd take absolutely forever. There's no way I'm going to do that. That's absolutely crazy. I'm just going to erase all that. That would take forever. So we got to be a little bit more clever here, because there's no way I'd give you a question that's going to take that long on this one. If you're super, super keen, you might actually notice that this is just something minus something else. Well, the only time in factoring that we have something minus something else is with difference of squares problems. Let's ask ourselves, can we square root this whole first chunk? Well, yeah, we can. 16 can be square rooted, and a plus 3 squared can be square rooted. So that's square rootable. What about the second chunk? Well, 4 can be square rooted, and a plus 1 squared can be square rooted. So this is actually just a difference of squares. It's just a really, really, really ugly looking one, right? So difference of squares works like this. Take the square root of the first piece. Well, the square root of this first piece would be 4 times a plus 3. plus the square root of the second piece. Well, the square root of the second piece would be 2 times a plus 1. Now multiply that by the same thing again, except this time we subtract these two pieces. So it'd be 4 times a plus 3 minus 2 times a plus 1. There's a lot to wrap our head around on this one, so I'll just kind of go over it again before I move on. Since we are subtracting two things that are square rootable, just square root the first piece, which is the square root of 16 is 4. The square root of a plus 3 squared is a plus 3, plus the square root of the second piece. Well, the square root of 4 is 2. The square root of a plus 1 squared is a plus 1. And you multiply that whole chunk, this whole chunk right here, by the exact same thing, just with a minus sign in there. So hopefully you see I just multiplied by the same thing again, just with a minus sign instead of a plus sign. Now, this is factoring, but it also wants us to find the roots, which is a bit of a pain. Finding the roots just says, where is this equal to 0? Well, at this point, we don't really have a choice. We have to multiply all these things through. It's just going to be a little bit of work. Let's multiply 4 through this. This is going to give me 4a plus 12. Plus, let's multiply 2 through here. Well, that'd be 2a plus 2. And then multiplied by, again, double dip this through, it'd be 4a plus 12. This one, we got to be careful because there's a minus sign here. And minus means we're like minusing this whole thing here. So it's minus, I'll put another set of brackets, minus 2a plus 2. And you're going to see why that bracket there is really important. Notice we're subtracting all of 2a plus 2. Well, here's what that means. First of all, I'll clean this one up because this one's not a big deal. 4a plus 2a is 6a. 12 plus 2 is 14. So that one simplified, no problem. This guy's going to be a little sneaky, though. 4a minus 2a, well, that would be 2a. 12 minus plus 2. Again, 12 minus plus 2, well, that's going to be 10. So 2a plus 10. Those brackets there kind of save you. If you didn't have the brackets there, you would have thought you were only subtracting the 2a, and you would have been adding 2 on there. It's not how it works because we're subtracting that whole chunk, right? But anyway, so we're finding the roots of this now. Set this equal to 0 and ask yourself, when is each of these chunks equal to 0? We'll start with this one here. 6a plus 14, when is that equal to 0? Well, it's minus 14 and divide by 6. That's going to be a equals negative 14 over 6. And I'll tell you the honest truth, I don't really want to write that as a decimal, so I'm just going to leave it right there. This one, however, we have 2a plus 10 equals 0. We got a minus 10 and then divide by 2, so that would be a equals negative 10 over 2. That one, though, I don't mind writing as a decimal because it's actually going to be a nice number. Negative 10 divided by 2 is negative 5. So those right there are going to be your roots. And again, that negative 14 over 6, I didn't write it as a decimal because it's a repeating one. I think it's like negative 2.3 repeating or something. It's not horrible, I guess, but it's still just, I don't really want to write that. Anyway, moving on. Next one, vertex form / square root method. Now, I'm going to be blunt with you. I really don't think there's much point in using the vertex form or square root method when you're given a standard form quadratic like this one. Like, honestly, like there's not really much use for that. There's other methods that would work better. The reality is, though, every now and then we will ask you to do this. So what that means is you're going to have to turn your standard form quadratic into a vertex form quadratic and then use your vertex form square root method. It's a huge pain. I think it's like a waste of time overall, but I'll do it anyway just because the question's here. We can follow along. You guys don't have to try this one on your own. Remember, to change standard form into vertex form, you just need to find your vertex. Your vertex can be found using x equals negative b over 2a, that little formula that we've been using quite a bit. That means this is going to be x equals negative 12 divided by 2 times 2. Or in other words, negative 12 divided by 4, well, that would be negative 3, right? So that's half of our vertex. Our vertex is negative 3 something, right? We got to find what that something is. To find that something, the y value, just plug in negative 3 into your function. So y is going to equal 2 times negative 3 squared plus 12 times negative 3 plus 20. Notice how I just put negative 3 in where each of my x's are. Solve this one very carefully. Don't feel like you have to run through it too fast. 2 times negative 3 squared, well, negative 3 squared is 9, so this is 2 times 9, plus 12 times negative 3, well, that would be negative 36. Now we still have that plus 20 just chilling there. This is going to be y equals 18 minus 36 plus 20, because there's no point in me saying plus negative 36. That's just awkward. Anyway, do this now. You can do this all at once. 18 minus 36 is negative 18. Negative 18 plus 20, well, that's y equals 2. So we know our vertex is the point negative 3, positive 2. Whew, all right, anyway, so what that means is we can change this to vertex form now. To change it to vertex form, remember vertex form looks like y equals a times x minus h squared plus k, where H and K are your vertex, and your A is just the same as your A value you had in standard form. So this, therefore, is going to look like y equals 2, because A was 2, according to this, 2 times x minus h. Well, x minus -3 is x plus 3 squared, and then plus k, so plus 2. Now we want to find the roots of this. So what we're going to do is we're going to say, yeah, I know it's y equals, but let's now just say equals 0, because if y is equal to 0, those are where your roots are. That's your x-intercepts, right? Let's solve for this. To do this, you basically got to get the squared piece all by itself. So let's minus 2 from both sides. This gives me 2 times x plus 3 squared equals -2. Divide by -2 now, we have, or sorry, divide by +2 now, because there's a +2 there. X plus 3 squared equals -1. And then we got to square root both sides here. But hey, wait a minute. If you try square rooting this, guess what's going to happen? You're going to square root a negative number. Can you square root a negative number? No, you can't square root a negative number. I can already hear you all screaming that, right? No, you can't square root a negative number. So what the heck? This is actually a broken question. So you can't square root a negative. So after all that work, there's no solution here. No solution. Well, that's kind of a buzzkill right there. So we had to change it to vertex form, then we never actually used it for anything. Oh well, so there's no solution, there's no roots. Joke's on us. And that is correct, by the way. So it is what it is. By the way, there's another thing. I don't know if you remember this, but there's something called the discriminant, which can be found by b squared minus 4ac. That little formula, b squared minus 4ac, tells you the nature of the roots. It tells you how many roots you have, right? If we test that on this one, b squared is 12 squared, which is 144, minus 4 times 2 times 20. That'd be 144 minus, that's 8 times 20, that's 160. That gives me -16. And because our discriminant's a negative number, that means we have no solution. So, mwaha, right? Joke's on all of us. It's almost like we should have started with that. But whatever. Anyway, we followed our orders. Long story short, if this had worked, like if this was a non-negative number, like a positive number, when you square root it, you're going to get x plus 3 equals whatever the square root of this is, and x plus 3 equals the negative version of whatever square root of that is. So if this number instead of -1 had been like 25, well, the square root of 5, most people would say, oh, that's just 5. But it could also be -5. That's where we go from there. But anyway, I'm rambling. Let's move on. Next one, you guys can definitely try this one on your own. Quadratic formula. This is like the absolute best way of solving a standard form quadratic, because it's just you plug the numbers in and you go to town on it. It's the most powerful way of doing this. It's awesome. I'm going to get you guys to give this one a shot. The formula's up in the corner. Pause the video here and I'll go over it in a second. All right, so we have our formula right there. There's not really a reason for me to jot it down a second time. Let's plug our numbers in. X equals -b. So -b would be negative 6.3. So this is positive 6.3 plus or minus the square root of negative 6.3 squared. You need the brackets around that because you're squaring the whole negative 6.3 plus 4 times 1.2 times 2.6. That's 4ac. And then all divided by 2 times a, so 2 times 1.2. I always like cleaning this up before I go any further. I like cleaning up all the square root stuff here first. So this is 6.3 plus or minus the square root of, if you put all this in your calculator, you're going to get the square root of 27.21 roughly, all divided by 2 times 1.2. Let's be honest here, you can just simplify that to 2.4. Now you know what to throw in your calculator. This plus or minus thing just means do it once if you add, and then do it another time where you subtract. So I'll start with 6.3 plus the square root of 27.21 over 2.4. I'll call this like x plus. So if I add these together, my answer to the nearest hundredth would be 4.80. So there's one of my roots, one of my x-intercepts, right? And then I'll do it again. If I subtract, I'll just call it x minus. If I go 6.3 minus the square root of 27.21, all divided by 2.4, you get 0.45. Whew, all right, that's a lot. All right, so we got 2 word problems to do here. We're almost done. Let's get this done. So here's the first one. Ryan wants to make a fenced-in area along the side of his house. There's no need to put the fencing along the side of the garden that touches his house. If Ryan has 26 feet of fencing, what is the maximum area of his garden? What dimensions would it have? So we're looking to maximize the area of his garden. We got to assume that the garden is going to be like a rectangular shaped garden. Now remember, he doesn't have to put fencing along the side of the garden that touches his house. Draw a picture on this one, pause the video here, give it a try. All right, so I'm going to go over this one now. Let's say this is the house, and here is his rectangular fenced-in garden. Now, there's a little bit of a trick here. Let's suppose we call this side length W for width. If this is width, this is also width. This side, however, there's no guarantee it's the same. I'll call it L for length. Now, we know we have 26 feet of fencing. So we'll say W plus L equals 26. Or in other words, because W plus W is kind of silly, you might as well just say it's 2W plus L equals 26. Now, what we want to find is the maximum area. Well, the area of a rectangle is just length times width. But we don't want to use all these variables, right? We don't want to have too many variables going on here. So let's use this other situation we came up with over here, the 2W plus L is 26, to make an expression representing one of these variables. I think we could probably all agree it's easier to get L by itself. Let's just minus 2W on both sides. So L is 26 minus 2W. Take this value, 26 minus 2W, and replace L with 26 minus 2W. Watch what happens. We got A equals 26 minus 2W times W, so length times width. This 26 minus 2W is just your length, right? So we just replaced length with 26 minus 2W. Might as well double dip this through. So take W, double dip it through. This is going to give me A equals 26 times W is 26W, minus 2W times W is 2W squared. I don't like how this looks because it's nice to have the squared out in front, so I'll just rearrange this. A equals negative 2W squared plus 26W. And if you really care to make it look like standard form, you can say plus 0 on there as well. Notice it's A squared plus B squared. Sorry, AX squared plus BX plus C. We got a standard form quadratic going on here. Now, here's where we kind of laugh. Nowhere in this question does it say we have to solve this algebraically, because otherwise you'd have to like do an adapted sum product rule or use the quadratic formula. But instead, I'm just going to take this quadratic right here, namely this part of it. I'm just going to throw it in my graphing calculator and see what I get. So if I throw this in my graphing calculator, I'm going to get a width, so W, or in other words, my X value here, W equals about 6.5 feet. Oh, I should really mention what I'm actually looking for there. For a maximum area of the garden, when you graph this, what you're actually looking for is you're looking for your maximum value. So like this, because if this is your area and this is your width, we're looking for the maximum area you can find. So the maximum area I found was at 6.5 feet for the X, which is your width, right? So this is the width that we'd have to make it. His garden would have to be 6.5 feet wide. We also want to find the length, and we also want to find what the area would be, because it says what is the maximum area of the garden and what dimensions would it have. We'll start with the dimensions. Since the width is 6.5 feet, just plug that into our L formula. So L equals 26 minus 2 times 6.5. Well, that actually just gives me L equals 13 feet. And then if you really, really want, you can just take, your width that you found for this and basically like plug it back into your function. Long story short, you're going to find your maximum area equals about 84.5 square feet. So hopefully that makes some sense. Basically what we're doing, because it was a maximum area, I should have explained that first. The maximum area is your vertex, right? So it's your maximum point up there. It is not your x-intercepts. That's where we'd have 0 area technically. We're looking for our maximum area on this one. All right, one last question. This one I'm not going to get you guys to try on your own because it's a little different than anything we've seen, but I'll show you the trick behind it. Let's suppose Megan is 3 times older than Carissa. So that's like right now. So right now, Megan is 3 times older than Carissa. In 10 years, the product of their ages, so if you multiply their ages together in 10 years, the product of their ages at that time will be 192. How old are they now? Let me show you how I'd go about doing this. Let's suppose we say Megan's age is M, Carissa's age is C. Right now, we know Megan is 3 times Carissa's age. So M equals 3C. We also know that in 10 years, the product of their ages will be 192. Well, how old would Megan be in 10 years? Well, let's see. If Megan is M years old right now, in 10 years, she'd be M plus 10. Product means multiply. So we're going to take her age in 10 years, and we're going to multiply it by Carissa's age in 10 years. Well, how old will Carissa be in 10 years? Well, if her age right now is C, then she'd be C plus 10 in 10 years, right? And we know that the product of their ages at that time will be equal to 192. But we're suffering from the same kind of problem that we've had before. We have 2 different variables here. and that's not exactly great. We can fix this, though, with understanding that Megan's age is just 3 times Chris's age, this right here. So we can replace M with 3C. So watch what happens if I do that. It'd be 3C plus 10 times C plus 10 equals 192, right? So if we have that, what we'll just have to do is now multiply it through using, like, I call it FOIL, basically. Excuse me, sorry. This is where I multiply my first term. You know what? I'll actually just take this real quick, change it to red. I'm going to take this first term, multiply by this first term. So 3C times C is 3C squared. Then I'll go 3C times 10. That'll be plus 30C. And then I'll go 10 times C, which is going to be just plus 10C. And then I'll go 10 times 10, which is plus 100. And this still all equals 192. Just to slow down here to show you what I did, basically, all I've done is I've recognized that Megan's age in 10 years times Carissa's age in 10 years is 192. Then I take the fact that Megan is 3 times Chris's age and I plug it in for M, so I don't have more than one variable. Now I double dip it through because I want something to look more like a standard form. If I clean this up by adding all of my variables together, this gives me 3C squared plus 30C plus 10C is 40C plus 100 equals 192. And we can go one final step more. If we set one side equal to 0, we can solve this using our graphing calculator. So I'll minus 192 on both sides. This gives me 3C squared plus 40C minus 92, because if I go 100 minus 192, that gives me minus 92, and this now equals 0. Whew, long story short, we can plug this into our graphing calculator, 3C squared plus 40C minus 92. Of course, your graphing calculator needs to use X instead of C, but we can plug that in our graphing calculator and we can find the intercepts, because where it's equal to 0, if you think about it, that's where Y is equal to 0. Those are your intercepts. Now, if we have any negative ages, like over on this side, that doesn't make any sense. You can't have a negative age. So if we find anything like that, we'll just have to ignore it. I'll let you plug that in your graphing calculator real quick. You actually might want to pause the video here. Plug this function in your graphing calculator and find the x-intercepts. And now I'll go over it. So hopefully when you did this, your graphing calculator would tell you that in this, you're going to get Carissa's age. So C equals 2, right? That means Carissa's age is currently 2, right? Because it's saying how old are they now? So we wanted to find C. So Carissa is 2 years old. I'll maybe even like list that, label that there, Carissa, perfect. And we know Megan is 3 times Carissa's age. So what's Megan's age? Well, Megan would be 3 times 2. Megan is 6 years old in this case. Perfect. I don't know why on earth we'd ever have a real world situation like this where you have to like solve a puzzle to figure out how old some kids are. But hey, you know what? It's the journey that counts, right? We had fun along the way, right? I don't know. Anyway, it is what it is. So for practice, chapter 4 assignment, remember you can complete that. It's due a little later this week. If you need extra practice, those questions in your textbook might help. And then chances are tomorrow morning, we're going to have an exit slip, or rather tomorrow, not morning, I guess tomorrow, beginning of class, we'll have an entrance slip. So just be prepared for that. Obviously, it won't be for marks or anything. If you need any help, though, please try to let me know, or at least reach out to others. Best of luck.